Hi, good evening, everyone. Shall we start?
Good evening, sir.
Hi, am I audible?
Yes, sir.
Yeah, okay. Okay, good evening, everyone, and welcome to this revision session for the content of week two of Gen AI concepts. Okay, so we will start. Thanks, everyone. Okay, okay, okay. So I will start with the thing which we had arrived at after week one. So please stop me anywhere if you're not understanding the concept. So we had arrived at week one, we had arrived at the lowest bound of the divergence. Okay, and this we had found out that the divergence lower bound that it has to be equal or more than the maximum of expectation of tx um, in the domain of px minus e p theta f star tx, which is the conjugate. This is the conjugate. So is this okay? From here we start. Is that okay, Nitish?
Yes, sir. Yes, sir. It
Okay.
is okay.
Yeah. So this was the culmination of week one. We had arrived here. Now, but our objective was to find, to minimize the theta, or to find that theta which minimizes this divergence. That divergence is denoted by this. So if you put it like this, then it will become your objective, or the optimization problem becomes that we have to find the theta to minimize this divergence, but this is the lower bound of the divergence. This is the lower bound. So it has come from here. And the lower bound, it is again an optimization problem that we have to maximize. Okay, so this is a function tx, and this is a conjugate of tx. So we have to maximize this. So now we also know that our neural networks, they can approximate any function. So this tx which is there, this can be a neural network. This we remember from our deep learning course, that from the approximation theorem, that neural networks can approximate any function. So this set of functions which was there, this is the t, this is all the set of functions, and this is the tx we have to find, which maximizes this. So I can write that now the objective becomes that theta star and w star is the argmin of theta, and maximizing with relation to w, where this t which is there, this tx which is there, now this can be written as twx, means it is a neural network with weights w. Is this okay with everyone, this concept?
Yes,
Pooja?
sir. It is okay.
Yeah, okay, good. So now we have replaced now this tx with a neural network. So this is twx, and here it comes the conjugate of this twx. Okay, so your loss function becomes this. So I will write here r min theta. So this is your loss function. Okay, so this is number two. Okay, now, like a professor covered in the lecture, that it is a saddle point optimization. Why it is a saddle point optimization? Because we are finding the theta which minimizes this function, whereas we are finding a w which maximizing this function. So that is known as a saddle point optimization. And it is adversarial in nature, because one is trying to minimize the function and another is trying to maximize the function. So that's why it is known as adversarial in nature. Now the domain which is there, domain of tw of x is such that it takes the x and it passes to the domain of f, the domain of f which is there. Now this twx also can be written as this sigma f and vwx, where vwx is a neural network and its output is a real number. Okay, so if we draw the visually, so this is like this, that this is VW of X. It takes X and its output is in the real number, and then it passes through an activation function, the sigma of F. Now this sigma of F is specific to your divergence, specific to F divergence. So whatever the F divergence you are selecting, then it is specific to that, and its output will be in the domain of F. So this entire TWX which was there, we can write down. So this is entire your TW of X. So we have written down like this. So I've covered, written the same thing. It is taking X, passing through a neural network, and this neural network is giving a real number. Therefore, this output layer will be a linear layer here, single MLP. Then it passes through this specific activation function, and then it gives the in the output in the domain of F is the function. So now we can write this loss function in the same. So this was our TW of X. So we have replaced this here, and this is our TWX. So we have replaced it here. So this is number 3. Okay. Now from here, now, so this was for this is a function, this we have to remember, it is for all F divergences. Okay, for all F divergences, this is the general formula. Now, when we come to GAN, that is the generative adversarial network. So in the GAN, the F divergence FU, which is there, we use U log U minus U plus 1 log U plus 1. So this is an important thing to remember, that in the GAN, this is the F divergence. And for this F divergence, the activation function which is there, which I covered earlier, it has to be specific. This is the activation function. So this we have to remember. So U log U minus U plus 1 log U plus 1 is the F divergence. And the activation function is minus log 1 plus e to power minus V. And if we put this FU, so our function, if we remember, so our idea was to arg min theta max of W, and it had become expectation over Px in the domain. This was sigma F of VWX, is there, and this becomes minus expectation of P theta F star of sigma F VWX. So this was, now if we put this function which is there and we try to find the conjugate. So I have done this, how to solve this. So here, so in the GAN, sorry, this FU is this function domain. Now we find F star theta, which is the conjugate. So conjugate is nothing. This is the formula for the conjugate. It is UT. Just give me a minute. हेलो, हाँ सीमा, मेरी कॉल चल रही है. आई विल गिव यू कॉल आफ्टर हाफ एन आवर. ओके गुन्नू बेटा. Okay, so this is the how we find the conjugate. F star T is so max UT minus FU. So when you replace this FU here, this will become U plus 1 log U plus 1. This is minus, so this becomes this, and this becomes UT. Now you differentiate this F star T with respect to U, and then we get a value in the relation with U. So we get U is equal to 1 over e minus t minus 1. And then again, when you put this value of u in f star t, so that is the time when we get this f star t is equal to minus log 1 minus e to power minus t. So this is here. Okay, so this is the one which professor had covered. So your conjugate becomes minus log 1 minus e to power minus t. Now see, this is minus and log is always positive. So therefore, the domain of this f star t is r minus. So this is the thing. So this has come, only we have to remember only this part, f divergence. From there we can calculate the f star t. And we have to remember that for this f divergence, the activation function is minus log 1 plus e to power minus v. Now with this, if we replace this in our loss function, so loss function becomes again r min theta max w. Now it becomes log dwx log 1 minus dwx. So this is the thing which has been given in the standard GAN papers. Standard GAN paper, if you read that. So in that, this is given. However, the professor has covered elaborately how it has come. So all these things have not been given there. So this is the standard GAN equation. And where the dwx is nothing, dwx is equal to 1 over 1 plus e to power minus vwx. Vwx is a neural network. And this, if we see, this is a sigmoid function. And sigmoid function, we know that it gives values between 0 and 1, including 0. So now, if we try to see how it is working, so there is a, visually, this is a generator function. It takes a value z, which is coming from a normal distribution with mean 0 and variance 1. We pass it through a function z theta of z. So from here we are getting x cab, which is coming from p theta x. So this is a generator we generate. And in the discriminator, this is x. We are passing through this neural network, and then we are passing through this activation function. And this total is the dw of x. Now, how to train this? So we know that we have to minimize also and we have to maximize also. So for training this, I will just take here. So now the visual diagram has become like this. This is a generator. It takes values z belonging to normal 0 and I. This is z theta of z. It gives x cap, which is coming from p theta of x cap. And this is a discriminator. This is a discriminator. Here we pass x also, we pass x tilde also, and this is your dw of x, and this is the output, and output is between 0 and 1. So till now everything, this is clear with everybody? Any doubt till now here with anyone? Nitish?
So this is clear, sir, but why are we like using GAN after the first we covered, which was F divergence?
No. So idea is, okay, so again I will give the intuition why we are doing this. So the thing is like this: we have got some data points x1, x2, x3
Yes,
up to xn. Okay. Now we
yes,
know that they are coming from their IIDs, and they are coming
unknown
from
distribution.
some unknown distribution px. Okay.
Yes,
Now the objective is first of all to find like a px of x or approximate, and then to
yes,
sample from it.
yes,
Okay, so from to sample from it. So I will give you an example of GAN, for example, that, for example, you have got some 100 images. 100 images are
Yes.
there. Now, we don't know from what distribution they are coming. But now, if I give a single vector and I want to generate an image which should look like that it is coming from the same distribution.
Yes.
Okay. So that is the
Yes.
intuition. So for that, what we did, I will just go to the week one again, concepts. So these are the data points which are available to us, and they belong to R to power in the dom of D. Okay, they can be in any dimension xi
Yes.
coming from R to power D. Now we said that if we have got some function g theta of z, we know that neural networks which are there, they are capable of approximating any function, any
Yes.
distribution. So we said that if we pass, for example, z belonging to normal distribution 0 to I, and it gives a x tilde x cab, which is coming from p theta of x cab. So this is your generator.
Yes. Like
Okay.
taking samples from normal distribution and approximating, giving output some X
Yes. Yes.
cap.
Yes. Yes. And then we said, okay, that there is a divergence matrix, which we denote by d px p theta. Now we have to minimize this so
Yes.
that the p theta starts resembling px, then only we can generate. Then we
Yes.
can use this g theta which is there. Now it can be used to generate the
Yes.
samples which will be looking like that they're coming from px of x.
Yes.
So from there, our objective became that you have to arg min theta, which is doing this px of p theta.
Yes.
Okay. And from there, okay, if you go through the week one content, then this dx and dp theta was described like
Uh,
p
FP
theta
theta.
x f of px of x over p theta of x, and dx, it was integration.
Yes. Yes. Yes.
Okay. And then
Yeah.
whatever we took some steps because we cannot do it directly. Then we use the principles of statistics, that if we have
Because
got
we
some.
not because we don't know the real distribution.
Yeah. So we know from statistics that if we have got a function and if we have got a distribution, then it can be approximated as accepted of h of x over px.
Mm.
Okay. So this property we utilized, and from there what we did, we found the lower bound of this divergence matrix. So what we found that this d of px over p theta is greater than equal to arg max t of x, which is coming from uh, t functions, and this is expected of t of x px minus expected of p theta f star of tx. This was, okay, we reached, okay, in week one.
What's
Is
that?
that okay?
I did
So
Yeah,
not
it,
understand
okay, just
the
hold
last
on.
line.
so
Okay,
we are
so
getting lower bound of uh, from
uh,
the true samples.
yes,
Like
no. So just go through the week one recording. I think it is available. So utilizing this statistics principle, what we found out that d of this divergence, which is there, p of x
this.
and p theta, we found a lower bound over that. So this was arg of max px, which is belonging to a wide variety of functions coming from t, and expected value over px. This is tx. Tx is a function minus expected of p theta conjugate f star of tx. Okay, so this was the one which we culminated in week 1. Okay, so
Yes.
this you have to remember. Okay, and from
Yes.
there now we started week 2. So if you remember the first line here in the lecture, we are starting from this point. Okay,
Yes.
okay. So this again was the culmination of week 1. And now what we did, so we have found the lower bound on this divergence. So this divergence which is there, it has to be greater than equal to this. But our objective is to find, or we have to find the theta which minimizes this divergence. So if you combine both of them, so your optimization problem becomes, you find the theta which minimizes this function, the whole equation, and find tx which maximizes this equation. Is that okay?
Yes, sir.
Okay. Now from here, then what we did, so we said that this tx which is there, this function we can represent by a neural network twx, which has got a weights w.
Mm.
Okay, so it became
Yes.
now theta star w star is equal to, we replaced tx with this neural network twx. We did only this. Okay,
Yes.
okay, so your loss function became this. So this is a standard loss function. This is the loss function. And in the next step, what we did, we wrote that this twx which is there, it is a neural network. So instead of twx, so this was a twx, what we did, we broke down this into two parts. We broke down that it has got one function, for example, v of w of x. It gives a real number, and then we pass it through an activation function sigma f, which gives the output as per the domain of function. And this sigma f, the function which is there, it is specific to your f divergence. So in the week 1, we had seen different types of f divergence. Okay, so this is a generic equation. So now in this equation, we just replace this twx with this. So we got this. So this is the standard your VDM. Okay, till now here, now it is clear with everyone. Nitish?
Yes, sir.
Okay, so we are just replacing them in the mathematical equations. And then what we did, so this is a generic for all VDM problems. So this is our optimization equation. Now, one of the optimization we use in the generative adversarial networks. And in generative adversarial networks, what we do, we use the f divergence, which is f u is equal to u log u minus u plus 1 log u plus 1. And for this, the activation function which is there, it is minus log 1 plus e to power minus v. And the conjugate when we find, so conjugate comes minus log 1 minus e to power minus t. This is domain is r minus. So these are the steps again. So from here, we have started with GAN. Okay.
Okay.
Okay. So now we will start. So now this was the equation which we have found earlier of the VDM that we had to find. We have to find theta which minimizes this equation, and we have to find w which maximizes this equation. Now when you put this u for this GAN, the fu, so then you get this standard equation. The loss function is min theta max w expected value of log dw of x minus expected log 1 minus dwx, where dw is a sigmoid function, and in the denominator it is e minus vwx, which is a neural network. So this is for a GAN. Okay.
it basically give more importance to the real like distribution, which real samples like
Y- Yeah. So what is happening? The generator is generating,
yes,
okay,
and
and this
discriminator
and
is
discriminator is trying to, maximize the difference between the real and the fake one.
yes,
Okay. And when you keep on training, when you find the theta and W, then P theta and Px, they come very, very close to each other.
yeah,
And when you will generate now, it will look like that it is coming from the distribution Px. So,
yes, hmm,
so what we have done, we have not found the distribution Px of x, but we have found P theta, which is very, very similar to Px of x.
yes,
Okay. Now, now we go further. Okay. So this I've covered. This derivation, I will share this notebook with all of you, so you can see this derivation also. So now how we implement in practice. So in practice, we have got only these data points which are there,
yes,
and they belong to xi is belongs to R domain D. Okay.
mhm,
And our function or the optimization problem for W star is argmax of this function. So how do we train the discriminator? So what we do, we always pass samples in batches. We have seen in deep learning and in LLM also.
yes, yes,
So we say that for generator, the number of samples are beta 1, and for discriminator, we are passing beta 2. Is that okay?
yes,
Okay. So it means now your W star will become, so this is your expected value of Px of x. So log dwxi summation over b1, and you are taking average of 1 by b1, and this becomes the second part becomes 1 by b2 summation of log 1 minus dwxj. So this ixi which is coming, it is coming from the samples, and xj which is coming from g theta of z. This is understood?
yes, sir.
Okay.
जी,
Okay. Okay. So what do we do? We generate this xj from g theta z. We keep the theta which is there. For example, I'll just cover it here only. I'll cover here. So when we are training, for example, training of a of a discriminator. So first we write the function W star is equal to R max W, and this was P of X log dw of X plus E P theta 1 log of 1 minus dw of X, but this X is different. This is Xi and this is Xj. Okay.
yes,
Now,
yes,
when you are passing now in the samples in the batches, so it will become, for example, here you are passing beta 1 sample, so this will become 1 over B1 summation of log of dw xi, I is equal to 1 to B1 plus 1 over B2 summation of log 1 minus dw xj, j is equal to 1 to b2. This is okay?
yes,
Okay. So now how do we do this? Now how to see this pictorially? So this is coming from px, and this is coming from p theta. So this xi which are there, we have got points x1, x2 up to xn. This is
mm,
already given. They are available.
yes,
Okay, for example, I give you an example of 100 pictures. So I have got 10 pictures. Okay, 100 pictures are there. The dimension can be
Yes.
64 into 3.
Yes.
So what do we do? This is your generator. So this g theta of z, which is there, z I sample from normal distribution 0 to I, and I initialize my neural network. So this is a neural network.
Yes.
I can initialize with some theta.
Yeah.
Okay.
Weights are randomly initialized.
Yes. So from here now I will get g theta x1 x cap, or I can z1 g theta z2 up to z theta of beta 2. Is this okay? I've taken
Yes.
beta 2 samples.
Yes.
Okay. Now I pass through this. This is my dw of x. dw of x. So here I am passing this, plus I am passing the real samples which are there from this. So
Yes.
this is x1, x2 up to x beta 1. This I pass. So
Yes.
from here, now I'll get two things. I will get number one, I will
Degenerate.
get 1 by beta 2 summation of log 1 minus dw of xj.
Yes.
J
The
is equal
first
to
one.
1 to beta 2.
Degenerated ones.
Yes.
Yes.
And here I get 1 by beta 1 summation of log dw of xi, where xi is I is equal to 1 to beta 1.
Yes.
I got two components. So this is my forward prop. This is my forward
Or
propagation. Forward propagation. And now to update w, wt plus 1 will become wt plus alpha 1, which is the learning rate, and the loss function with respect to j theta w, and we have kept theta fixed with theta fixed. Is this okay? So your back propagation which is there, the back propagation which will pass, and it will only update w. This is back prop.
okay. Only update discriminator, not
Yes,
generator.
only it will only
Yes.
do updation of w.
Yes.
Is that okay, Pooja?
Yes.
Okay. So this is clear again. If you have understood this diagram and this concept, then you can easily
Yes.
code also. There is no problem.
Yeah, it's clear.
Okay. Yeah. So with the same concept now, we come to training of generator. Now generator is what? Generator is theta star is equal to r min theta expected of log of dw x. This is domain px plus expected p theta log of 1 minus dw xj. Now see this theta star, or now I can write down this also as 1 by beta 1 summation of log dw of xi, and this xi is coming from actual data points up to beta 1 plus 1 by beta 2 summation of log 1 minus dw xj, and this j is coming from your generator beta 2. So if you will take, so this is your theta star, or this. So remember this first part which is there, it does not depend on theta, on theta.
Yes. It doesn't depend.
Okay. So when you calculate the loss function, so theta star basically it depends only on this. Okay.
Yes.
Okay. So now pictorially, you see now this is your generator. This is g theta of z. This you have passed. So again, you have got g theta z1, g theta z2 up to g theta z beta 2. Now you pass it through your discriminator. Now keep this W fixed. This dW which is there, W is fixed. Is that okay?
Yes.
And you are passing these samples which are there, but these samples which are there, they don't make any difference to your loss function because this is only coming here. So what you will calculate here, you will calculate only 1 by beta 2 summation of log 1 minus dw of xj. So this you have passed, it has come. So this is your forward prop. This is your forward prop.
Forward pass.
Oh, okay, forward pass. But here, unlike the discriminator, when you do the back prop for updation, it will pass through this also and through this also to update the theta. So your theta t plus 1 is equal to theta t. You are minimizing, so it is minus. Learning rate is different, alpha 2, and your pass. This is the loss function g theta w, keeping w fixed. Is this okay?
Yes.
Okay. So this is the culmination of week 2. So again, I will just carry out a quick revision. So from where we started from the thing where we had finished in week 1. We had found a lower bound on the divergence, and we found that it is greater than equal to max of tx belonging to wide range of functions t, and expected tx is a function, domain is px, minus expected f star tx, which is the conjugate of tx, and domain is p theta. What now? But our original objective was to find the theta which minimizes this divergence. So when we put it, so our optimization problem becomes to minimize the theta, but to maximize that tx for this equation. Then we utilize that this tx can be represented by a neural network, which we call TWX, where the W are the parameters or the weights of the neural network. And then we said that TWX we broke down into two parts, one VWX and another sigma fx, where sigma fx is a divergence, f divergence specific activation function. And VWX is a neural network with the outer output layer as a linear layer, which gives output as a real number. So when you put this, so we got this equation. So now equation became min theta max theta, and instead of TWX, we replaced with sigma f VWX. It remains, everything remains same. So this is a generic equation for a VDM. Now from here, then we jump to GAN. And in the GAN, we use f divergence, which is there. We use f u is equal to u log u minus u plus 1 log u plus 1. And for this f divergence, the activation function is minus log 1 plus e minus v. And when we fit this fu, so we find the conjugate. So conjugate comes minus log 1 minus e minus t. And we put this in this equation. So we finally get the standard GAN equation. That loss function is min theta max w, expected log dwx minus expected log 1 minus dwx, where dwx is 1 over 1 plus e to power minus vwx. Vwx is a neural network. Now we try to find the solution for this optimization problem for both. So this px which is there, this is a discriminator, and this is p theta, this is a generator. And how do we do that? We have got now, when we come to the practical problem. In the practice, we are giving some data points. They are coming from PXX. Objective is to find to sample from it, and how we are doing. We train the discriminator. So we have to find W star and the same equation. So we pass through this discriminator or the from these data points we sample uh, B1 points, and we pass through this, we get the expected value, which is this. And for this from the generator, we get 1 by beta 2. So for W star, what do? We sample first Z from the normal distribution. We keep theta fixed and we get output beta 2 points. And then we pass it to the discriminator. And we are also passing the data points, B1 data points. So we get this part here, the second part here, and this is the forward prop. And for the back prop, we just pass it through the discriminator only, and we update the W. Since it is a maximizing problem, so WT plus 1 is equal to WT plus alpha 1, and the loss function or the loss gradient of this loss function. This alpha 1 is also known as the learning rate, or it is also known as a step size. Now for the training of generator, we minimize this equation total function with respect to theta. We find theta which minimizes this. So when we see the first part log dwxi, this does not affect the theta star. So we do only the second part. So what do? We keep this pass, we sample this generated data points, we pass through discriminator, we get 1 by beta to this. So this is the forward pass. And then for the backward pass, it passes through the discriminator and it also passes through the generator. And we update the theta t plus 1 is equal to theta t minus alpha 2 and gradient, loss gradient of the loss function. Since it is a minimizing problem, so we are subtracting. And alpha 2 is again, it is the learning rate or the step size. So here, this is the culmination of week 2. So in case anybody having any doubt, I can cover it again. Concepts or mathematical equations. Is it clear, Nitish, now?
You can cover like basic things, like broader things that is happening.
Okay, so broader thing. Okay, I will just cover it again. Okay.
The like it is very theoretical.
No, broader thing. So I'll tell you what is the application of this. So,
Yeah.
what is a practical application of this? So
Yes.
practical applications is like this, and it is used at many places. If you just Google it and GAN. So for example, you have got some 1,000 pictures. Okay.
Yes.
Like I told you. So these are 1,000 pictures you have got. Okay.
Yes.
And now, so remember on the internet or this chat GPT, how do they generate images and that person is not real at all?
They learn it from different distributions by like
Okay.
taking samples
Yes.
and training on them.
Yes. It is not training. So it is in the image, this, the GAN has got an application. So what do? So you have got, for example, you have got these 1,000 images which are there. Okay.
Yes.
And the dimension of these images is, for example, 64 into 64 into 3.
Yeah.
Okay. So this becomes your x1, x2 up to x1000. And it is, these are IIDs because we are assuming they are coming from the same distribution. Okay. IIDs coming from Px of x. And it is belongs to R3.
Yes.
Okay. So now objective is what? Objective is that I pass, for example, one vector, I just gives one z, and I want to generate an image which should look like that it is coming from the same distribution.
Hmm.
Okay. So for that, now what we said, that we make a
They are not
generator.
giving real samples, right?
These are the real samples, 1,000. But from here now
like
we have to approximate this distribution.
yes,
Okay. So we know that they are coming from some distribution, but we don't know. It is an unknown distribution. So there we utilize this, that we have got a generator and we have got a discriminator. Okay. And now this G theta of this, which is their Z, and this is dW of X. So we keep on finding this theta star and W star. Okay.
mm,
And now once we get this theta star, once we get optimal, so from generator, now you have to just pass one Z, this Z belonging to normal distribution, 0 to 1. And now I've got some weight taken here, okay, this theta star. So
yeah,
whatever I pass now, it will generate now a picture, which will look like that this is coming from the same distribution.
yeah, like the
Okay.
same image. It will not discriminator will not be able to
Yes.
like differentiate.
So it is a distribution. So remember, for example, I
Yes.
have passed like 1,000 people's image, 1,000 faces. So
Mm,
this will not give me one of the face from here, but it will generate one new face, which will look like that it is coming from the same P of X of X.
distribution.
Okay. So that is a broader thing.
Mm-hmm.
Okay.
And the px
Yes.
of x is a known distribution.
No. Px of X is an unknown distribution. We don't
Okay,
know. We have got only samples from that.
understood.
Okay. We have got some
P
samples,
theta,
for
P
example.
theta is also unknown, na, sir.
P theta is also unknown, but P theta, what we are doing, P theta is unknown, but we are approximating by using a neural network,
Yes.
because neural network has got a power that it can approximate any function. Okay, in the deep learning we had learned this.
Mm.
Okay,
And that we are minimizing between both
yes. So
generator.
yeah, so Mali, with respect to generator, we minimize the value of that function, and then the discriminator we maximize. We find the W which maximizes that equation.
Yeah.
So it's like the p theta is the distribution which is given by the model, and px is the distribution which we have assumed based on the sample.
Yes, it is an unknown distribution. What we are saying that we have
Okay.
got, for example, 1,000 data points are there. They are identical, independent distributions. They are coming from
Mhm.
the same distribution, but we don't know that distribution. We are calling it as Px of X.
Okay, we're just assuming.
Yes.
Okay.
The
We
expectation like
know.
lower bound was
Huh.
sir,
Huh, Nitish?
lower bound was coming from samples, right? Lower bound we are approximating expectation of both distributions by their
O-
samples.
Okay, lower bound was like this. This was sup max
Like
P
we
of
don't
X.
know the distribution, so we can't minimize the distributions divergence. So we are taking samples and giving in functions, I think, or and approximating like less. It
No,
is kind of divergence. I
what
think.
we did, we used the principles of statistics.
Yes,
Okay. And then we use the properties of the conjugates that, for example, F star of U is equal to FU. Conjugate of a
yes,
conjugate of a function is the same function.
yes,
Okay. And then we had utilized that if we integrate h of x, where h of x is a function, and for example, p of x, x is a distribution, and it can be approximated as ex expected px h of x. So these two mathematical properties which we had utilized to find this lower bound. So this is the lower bound.
mm.
Okay.
Okay, sir.
Yeah. Okay, I will urge all of you
Today,
go through the notes again and again. Try to get higher uh, intuition.
Yes, yes, sir.
Mathematics okay, will come on its own. Mathematics, it is like, class 10th or class 12th, you have to remember those 5 steps, 7 steps, but you should know what is happening behind okay, that, why it is coming like that.
Yes, yes,
Okay, so that we don't have to memorize. It will come on auto, intuitively.
yes, sir.
Chalo. Okay, then if there is no other question, can we call it off?
Yes, we
Yes,
can.
sir.
And the
Yes.
recording of the week one is available.
Yes, yes. Week one, I think it is available. Otherwise, I
Okay.
will put it.
Okay.
Thank you. Thank you for
Thank you
joining and
very
have a very
much.
nice day. Bye bye. Take care. Bye bye.
Bye bye.
Thank you, sir. Thank you so much.
Bye bye.